So we learned in the last section about taking derivatives of explicit functions. We had y equals something or f of x equals something, and everything on the right hand side would just be in terms of x, so we could just use those derivative rules. In this section, 3.6, we're going to talk about implicit differentiation and related rates. So you can see here, I have an explicit function. I just have y, or f of x, equals 4x cubed minus x plus 7 over x minus 3. So we'd use the power rule for this, and we'd use the quotient rule for this, and take our derivative. But what if we have functions where x's and y's are mixed together? So I have two choices. Sometimes I can solve for y, and it's not a big deal. Sometimes it's really hard to solve for y. But we're going to go through and be able to take these derivatives without actually solving for y. And what we're going to do is, at the end, we will take the derivative, that dy dx, and solve for that, and put it back together. So I have my first example here. Oh, I'm sorry. And we're going to be using the chain rule. So y is a function of x, and I have to remember that when I'm taking a derivative. So because it's a function in itself, I'm going to have to make sure that I have a y prime or a dy dx. So our first example, we have y cubed equals x. And I'm going to take the derivative of both sides without solving it for y. So d dx, because x is my independent variable of y cubed, equals d dx of x. So when I take this derivative over here for y cubed, I'm just working on this side for now. Then I'm using the power rule. The 3 gets multiplied out front, and I get 3y squared. And again, because y is a function of x, I have to use the chain rule. So I multiply that by dy dx. So this whole thing is the left-hand side of my function. The right-hand side, when I take the derivative of just x, I get a 1. So here's my right-hand side. So what I did here is put them back together. We have 3y squared dy dx is equal to 1. The next thing I need to do is actually solve for dy dx. So in this case, just divide both sides by 1 over 3y squared, and here is my derivative. But we could easily solve this problem explicitly for y. So if I have done that, I have y cubed is equal to x, and all we do is take the cube root of both sides, and we get y equals x to the 1/3 power, or the cube root of x. Now when I take the derivative, I just have my y prime, and then here the 1/3 gets multiplied out front, and then subtract 1 from the exponent, so I get 1/3 x to the negative 2/3. And I want to show you, even though they look very different, they are equivalent. So I have 1/3 x to the negative 2/3. If you go back to the original problem, y cubed was equal to x. So where I see that x, I'm plugging in y cubed. Multiply these two exponents. So 3 times negative 2/3 gives me y to the negative 2. And then bring that down, and we get 1 over 3y squared, which is exactly what we got for the other derivative. Alright, our next example. This is from the one that I written out on the first page. And I have x squared y plus 4x minus 3y plus 7 equals 5. So we're going to be using the product rule, and again the chain rule, for any time I see a y. So starting off with my x squared y. Using the product rule, I have x squared, and then I'm taking the derivative of y, so d dxy. And then I'm going to have y times the derivative of x squared. So that's the first term that I have underlined here. Then I have to take the derivative of 4x, take the derivative of 3y, the derivative of 7, and the derivative of 5. So each term is I'm looking at differently. Alright, so when you take the derivative of y, Using the chain rule, we'd get 1, and then because y is a function, then we get dy dx. So this term becomes x squared dy dx. And then over here, when I take the derivative of x squared, that gives me a 2x. So I have y times 2x, which is this term. Derivative of 4x is just 4. Derivative of 3y. So the 3 and then that y, again, because it's a function, becomes dy dx. And then we know the derivative of constants are just 0. So these last two terms are 0. My next thing is I can't leave it like that. I need to solve it for dy dx so I can actually know exactly what the derivative is. So we're going to subtract this 2xy and the 4. It came over to the right hand side. And then I have these two terms, and I'm going to write it here. I had the x squared times dy dx. And then I had the 3 times dy dx. So if I factor out a dy dx, then I have an x squared minus 3, and that equaled negative 2xy minus 4. So our last step was just divide both sides by x squared minus 3. And that's where we solve for this derivative. And you can take higher order derivatives for this. You can take the second and third derivative. And that's why you have to get it in the form of dy dx before you look at anything else. I'm going to do one more example before we look at related rates. So I have x plus y cubed minus 4xy minus 7 equals 10. So I have my first derivative. I can take the derivative of x, and it's just going to give me a 1. The y cubed, that 3 has to come out front, so it's going to be 3y squared. And then because y is a function, it's times dy dx. This minus 4xy, I have to use the product rule. So I'm going to do minus 4x times the derivative of y, which is dy dx. And then we have the y times the derivative of negative 4x, which just gives me a negative 4 times y. And then the 7 gives me a 0, and the 10 gives me a 0. So the terms that don't have a dy dx, I have to move to the other side. So I'm going to subtract 1 and add 4y. So these terms I took care of. And now what's left, they both have a dy dx multiplied by them. So I'm going to factor that out. And I'm left with 3y squared there. And a negative 4x there. Last step, divide both sides by that. And my derivative is 4y minus 1 over 3y squared minus 4x.